When NASA's probe finally captured the first close-up images of 3I, Atlas, scientists froze. The surface wasn't natural. Hexagonal patterns covered every inch. Then the object did something that made every researcher go pale. In 12 seconds of footage, it revealed what it truly was, and then the spacecraft vanished without a trace. What those final images show will change everything we thought we knew about what's really out there. Space agencies had debated for weeks about whether the risk was worth the potential discovery. NASA and the European Space Agency eventually agreed to repurpose a probe that was already in the region, adjusting its course to match the object's speed and direction. The window of opportunity was extremely narrow. The object was moving faster than anything humanity had previously attempted to track at close range, and the alignment would only last for a few days. Engineers calculated that a direct landing would be impossible, given the speeds involved. Instead, they planned a flyby approach where the spacecraft would coast alongside the object at a safe distance, close enough to capture detailed images but far enough to avoid collision. The probe carried a suite of cameras and sensors designed to map the surface, measure temperature variations, and analyze any gases or particles being released into space. When the first images began arriving at mission control, the initial reaction was confusion. Scientists had expected to see something familiar, perhaps similar to other comets that had been studied before. Objects like Halley's Comet or 67P Churyumov-Gerasimenko typically show rough, irregular surfaces covered in dust and ice, with occasional jets of vapor streaming away as solar heat warms their frozen cores. But the images coming back from 3I Atlas showed something completely different. The surface wasn't the chaotic jumble of rock and ice that defines most cometary nuclei. Instead, it displayed an organized pattern of large, hexagonal plates that overlapped each other like tiles on a roof. Each plate measured several hundred meters across, and they alternated between dark slate gray and pale silver tones. The boundaries between these plates weren't rough cracks or fractures, they were clean seams that appeared almost machined in their precision. As sunlight hit these seams at certain angles, something unexpected happened. Brief flares of light would pulse along the boundaries, lasting only seconds before fading away. The effect suggested that material beneath the surface was somehow conducting energy, either heat or electrical charge, though exactly how remained unclear. Instruments detected dust streaming away from these seams in narrow, focused jets rather than the broad, diffuse clouds normally seen around comets. What made this even stranger was how the dust behaved after being released. Instead of simply drifting away into space as would be expected, the particles curved back toward the object, following invisible pathways before settling onto the surface again. Analysis of the magnetometer data revealed why. The object was generating its own magnetic field, strong enough to influence the trajectory of charged dust particles. This was highly unusual. Small, rocky, or icy bodies shouldn't produce significant magnetic fields on their own. That typically requires a molten metallic core, active geological processes, or, in some cases, remnant magnetism frozen into ancient rocks. The magnetic field itself had peculiar characteristics. Rather than being stable and uniform, it pulsed gently in rhythm with the object's rotation, which took approximately 9 hours to complete. Each rotation brought the same pattern of magnetic intensity, suggesting some kind of internal structure was responsible for generating it. As the probe continued transmitting images, more details emerged that challenged conventional explanations. The surface features didn't look like they had been shaped by random impacts or gradual erosion from solar radiation. Angular ridges crossed the surface at precise diagonal angles, meeting at junctions that formed consistent geometric patterns. In some areas, flat depressions resembled inset panels, rather than the bowl-shaped craters that asteroids and moons typically display after being struck by smaller objects. Researchers examining the high-resolution imagery noticed that certain areas reflected light differently than others. Some regions showed a crystalline quality to their structure, but the alignment was too uniform to be natural crystallization. It looked more like layered material that had been arranged according to some organizing principle. Under enhanced exposure settings, faint reflective streaks appeared along certain ridges and boundaries. Spectral analysis of these features revealed an unusual chemical signature that didn't match any known mineral compounds. The readings fell into an intermediate range where organic carbon molecules seemed to be bonded with metallic elements, creating hybrid compounds that weren't found in ordinary geological samples. One of the most puzzling observations came from watching how the surface responded to sunlight. As the object rotated and different areas were illuminated, narrow lines began to glow faintly across the surface, forming grid-like networks that spanned entire regions. These patterns would appear when sunlight struck them and then fade as the area rotated back into shadow. Thermal imaging suggested the surface was transferring heat in a selective, almost directional manner, with warmth moving from one region to another in waves rather than spreading uniformly as would be expected from passive heating. The pattern of heat distribution didn't follow any known geological process. It resembled something more akin to how electronic circuits manage thermal loads, or how biological systems distribute metabolic energy through networks of vessels. Some scientists tentatively compared it to vascular flow, though nobody was suggesting the object was alive. It was simply the closest analogy for describing what the data showed. Adding to the mystery were certain shadows on the surface that didn't behave as shadows should. Some depressions remained completely dark even when facing directly toward the sun. Rather than reflecting light, these areas seemed to absorb it entirely. Spectroscopic measurements of these zones showed dramatic drops in readings across all wavelengths, as if the surface material in those locations was specifically designed to trap incoming radiation. Mission scientists began comparing the data with observations from other well-studied interstellar or unusual objects. Comet Borisov, which visited our solar system in 2019, had shown some peculiar characteristics but nothing like this level of surface organization. Oumuamua, the cigar-shaped object detected in 2017, had raised questions because of its unusual acceleration and tumbling motion, but it was never observed closely enough to reveal surface details. Classic comets like Hale-Bopp displayed spectacular tails and outgassing, but showed typically chaotic surface geology. 3I, Atlas fell into a category of its own. It combined characteristics that shouldn't coexist. The surface appeared frozen and unchanging in form, yet it was actively redistributing energy in patterns that suggested function rather than random physical processes. Whatever forces had shaped this object, they had left evidence that went far beyond anything that could be explained by natural erosion, impact weathering, or thermal cycling over millions of years, drifting through space. As the spacecraft adjusted its position to pass beneath the object's equatorial region, the imaging system captured a sequence that would fundamentally change how researchers understood what they were observing. The probe's trajectory brought it to an angle where sunlight struck the underside of the surface obliquely, illuminating features that had remained hidden in previous passes. What appeared in those frames left analysts struggling to find adequate explanations. Beneath a thin layer of dust and carbonized frost, the object was reflecting light from within itself. This wasn't the scattered, diffuse glow that occurs when light penetrates translucent ice. Instead, it was a coherent gleam that appeared with a slight delay, milliseconds behind the initial sunlight exposure, as if something below the surface was actively responding to the illumination. Frame-by-frame analysis confirmed the effect was real and consistent across multiple observation cycles. Using polarized filters to isolate the phenomenon, researchers determined that the glow originated approximately 30 meters below the visible crust. The light came from what appeared to be a continuous layer of dense material, extending across much of the object's interior. Spectroscopic analysis of this buried layer revealed a chemical signature consistent with hydrated silicate minerals, compounds that only form in the presence of liquid water. This presented an immediate problem. Comets do contain water ice, but it remains frozen in the extreme cold of deep space. Finding minerals that require liquid water for their formation, preserved in a stable layer deep within an object that had spent potentially millions of years in interstellar space, contradicted every model of how these bodies should evolve. The subsurface layer displayed other unusual characteristics. Its thickness remained remarkably uniform across all measured sections, and its reflectivity was consistent regardless of which portion was being examined. More intriguingly, the layer exhibited subtle phase shifts as the object rotated. These shifts created interference patterns similar to ripples produced by sound waves moving through water. The implication was that the material might be vibrating or oscillating at frequencies too low to detect directly but visible through their effects on reflected light. When scientists correlated these optical observations with magnetic field measurements, they discovered something extraordinary. Every time the buried layer brightened, the magnetometer readings spiked proportionally. The two phenomena moved in perfect synchronization, suggesting they weren't independent processes but parts of a connected system. Light and magnetic energy appeared to be cycling through the object's interior in a coordinated pattern, as if the structure itself was regulating these flows for some purpose. The spacecraft's next objective was to conduct detailed spectroscopic analysis of the surface composition. The probe transmitted electromagnetic pulses across multiple frequencies, recording how different materials absorbed or reflected each wavelength. The results added another layer of complexity to an already baffling picture. Every individual element detected was ordinary enough on its own. Carbon, oxygen, silicon, iron, nickel, and various other compounds commonly found in space, but their proportions made no chemical sense when considered together. The isotopic analysis revealed particularly strange patterns. Isotopes are versions of elements with different numbers of neutrons in their atomic nuclei. They form under specific conditions related to temperature, pressure, and radiation environment. Scientists use isotopic ratios to determine where and when materials originally formed. The hydrogen isotopes found on 3I Atlas were significantly heavier than those found in any known comet. This suggested the water ice had formed in an environment exposed to intense radiation, likely in a region far from any active star, where cosmic rays would have altered the hydrogen over immense spans of time. However, the carbon isotopes told a completely different story. They were unusually light, with ratios similar to carbon found in Earth's biosphere. This created an impossible contradiction. Heavy hydrogen implies formation in the cold, radiation-soaked depths of interstellar space. Light carbon suggests formation in the warm, protected environment near an active star, possibly even within a planetary system. These two signatures shouldn't coexist in the same sample unless the materials had been gathered from vastly different locations and somehow combined. The conductivity measurements added yet another anomaly. The probe sent low-frequency electromagnetic pulses toward the surface to measure electrical resistivity, a standard technique for determining subsurface composition. In normal circumstances, these signals scatter randomly as they interact with various materials, but the return signals from 3I Atlas didn't scatter. They came back in organized patterns with identical delay times that repeated at exact mathematical intervals. The effect mimicked what happens when electromagnetic waves bounce through layered conductors or interact with antenna arrays specifically designed to resonate at particular frequencies. A randomly assembled chunk of rock and ice shouldn't return electrical signals with mathematical precision. Thermal mapping provided additional evidence that something highly unusual was occurring. The probe's infrared sensors tracked how different regions absorbed and released heat. On a normal object, areas exposed to sunlight warm up predictably, and shadowed areas cool down. Heat spreads gradually from warm regions to cooler ones until equilibrium is reached. But 3I Atlas didn't follow these rules. Certain zones absorbed solar radiation without showing any corresponding temperature increase. Adjacent areas released heat, despite having no apparent energy source. The pattern suggested deliberate energy management, with some regions cooling at the exact moment others warmed, like nodes in an electrical circuit alternating their charge states. Mission logs described this behavior as thermal inversion of non-natural origin. Engineers noted that the heat distribution resembled load balancing systems used in spacecraft and satellites to prevent overheating of sensitive components. But this was supposed to be an ancient chunk of ice and rock that had been drifting through space for potentially billions of years. The probe's final major discovery during this phase came from ground-penetrating radar scans. The spacecraft carried instruments capable of sending radio waves into the surface and analyzing how they bounced back. Different materials reflect radar differently, allowing scientists to create three-dimensional maps of subsurface structures. When these scans were processed, they revealed something that shouldn't exist in an object of this size. Deep beneath an unremarkable crater near the object's northern pole, the radar detected a massive hollow space. The cavity began roughly 400 meters below the crater floor and extended laterally for nearly 5 kilometers. Its dimensions and geometry were unlike anything seen in natural celestial bodies. The internal walls reflected radar signals with unusual clarity, forming what appeared to be right angles and curved corridors. Natural geological processes don't create such features inside small bodies. Impact craters can create fractures and voids, but they're irregular and chaotic. This cavity had structure. The walls appeared to be reinforced by materials that were denser and more cohesive than the surrounding rock and ice. Radar signals indicated compositional differences, suggesting the chamber walls were made from substances more durable than ordinary silicate minerals or water ice. It was as if the interior had been deliberately excavated and then stabilized. Even more perplexing was what happened when the radar pulses bounced through the cavity. They created harmonic feedback, amplifying themselves in a way that caused the instruments to register signal levels far higher than what was transmitted. The echo didn't just bounce back randomly. It grew louder and more coherent with each pulse, eventually forming a standing wave that repeated itself exactly every 3.7 seconds. This kind of resonance requires very specific geometry. The cavity was acting like a musical instrument, vibrating at its natural frequency in response to the radar stimulation. When technicians analyzed the waveform structure, they found secondary modulations embedded in the signal that didn't correspond to any known electronic interference pattern. The signal, when converted into a visual representation, formed a double helix, a spiraling interference map rotating around a central void. This level of internal organization suggested the cavity wasn't just empty space. It was a chamber designed to resonate at specific frequencies, possibly storing or channeling energy in ways that defied conventional physics. The accumulating evidence pointed toward a conclusion that most scientists were reluctant to state explicitly. 3I Atlas wasn't behaving like a natural object shaped by random cosmic processes. Every measurement suggested purpose and design, from the organized surface patterns to the precisely tuned interior cavity. Whatever this object was, it appeared to have been constructed by processes that went far beyond anything geology or astronomy could explain. In the hours following the subsurface radar scans, the spacecraft's optical sensors began registering subtle changes in the way light reflected off the object's surface. At first, mission controllers attributed the variations to sensor drift or changes in solar angle. Instruments operating in the harsh environment of deep space occasionally require recalibration, and minor fluctuations in readings are common. However, by the time the probe completed its second full orbit around 3I Atlas, the patterns had become too consistent to dismiss as instrumental error. Across the sunlit hemisphere, entire sections of the crust were changing color. The muted gray tones that had characterized the surface during initial observations were gradually shifting into shades of blue and green. The transformation started faintly, barely detectable in the early images, but intensified with each subsequent rotation. Spectroscopic analysis confirmed that this wasn't a trick of light or a chemical reaction caused by prolonged solar exposure. The color change was happening in real time, occurring over hours rather than the geological timescales normally associated with surface weathering. The spectral signatures from these transforming regions revealed the emergence of new chemical compounds. Hydrated minerals that hadn't been present in earlier scans now showed clear absorption lines in the data. Complex carbonates and traces of nitrogen compounds were forming along freshly exposed ridges and fracture lines. The timing was impossible to ignore. The surface transformation had begun within 20 minutes of the radar pulse that had mapped the internal cavity. The sequence of events suggested a direct connection between the probe's active scanning and the object's response. As the color shift progressed, another change became apparent. The surface was shedding material. Fine layers of dust that had presumably accumulated over millions of years were being released into space, revealing structures beneath that hadn't been exposed to sunlight in eons. These newly uncovered features were highly reflective, catching sunlight and bouncing it back with an intensity that caused brief glare artifacts in the imaging sensors. The exposed material looked polished, almost metallic in places, showing none of the weathering or degradation expected from ancient surfaces. When direct sunlight struck these revealed structures, they didn't behave like passive rock or ice. The surface temperature in those specific areas rose sharply, and then stabilized at levels well above what solar heating alone could maintain. Thermal equilibrium calculations showed that the object should have been radiating away excess heat, gradually cooling until it matched the balance between absorbed sunlight and radiated infrared. Instead, the temperature held steady at an elevated level, implying that something beneath the surface was actively regulating thermal output. The spacecraft's particle detectors began registering increased activity. A steady stream of molecules was escaping from the region around the polar crater where the internal cavity had been discovered. Mass spectrometry identified the composition as primarily hydroxyl radicals and carbon dioxide, both common around comets as ice sublimates under solar heating. But mixed within this familiar outgassing were unexpected compounds. Ammonia and various cyanide molecules appeared in concentrations that seemed disproportionate to what should be present in ordinary cometary ice. Chemical analysis of these trace compounds revealed something remarkable. When ammonia, cyanide derivatives, and simple carbon molecules mix in specific ratios and are exposed to ultraviolet radiation from the sun, they undergo reactions that produce amino acid precursors. These are the fundamental building blocks that, under the right conditions, can assemble into the proteins essential for life. The same chemical pathways that led to the emergence of biology on Earth billions of years ago were apparently playing out on the surface of this mysterious object. The implications were staggering. The material being released wasn't random debris sublimating from frozen deposits. It represented a specific mixture of organic chemistry, the kind that scientists search for when looking for potentially habitable environments. The fact that it appeared immediately following the radar scan suggested the probe's examination had triggered some kind of response, as if the object had been waiting for external stimulation. Mission scientists debated whether to classify what they were witnessing as activation or simply as a complex physical response to energy input. The distinction mattered because one explanation involved known physics, while the other implied something far more speculative. If the radar had simply heated internal ice deposits enough to cause outgassing, that would be unusual but explicable. If instead the object was responding to the probe's presence in a coordinated way, releasing specific chemicals and altering its surface characteristics, that suggested a level of functional complexity that didn't fit any natural model. The surface changes continued to accelerate. New spectral lines appeared in the data every few hours as additional compounds emerged or transformed under solar radiation. Regions that had been dark and dormant began showing thermal signatures, indicating subsurface activity. The hexagonal plates that covered much of the surface developed a faint luminescence along their borders, as if energy was flowing through the seams between them. This glow was subtle, visible only in enhanced imaging, but it traced pathways across the surface that connected the polar regions to the equatorial zones in branching networks. Magnetometer readings tracked corresponding changes in the object's magnetic field. The gentle pulsing that had characterized the field during earlier observations became stronger and more complex. Instead of a simple rhythmic fluctuation, the magnetic signature now showed multiple overlapping frequencies, creating interference patterns that varied depending on which region of the surface was being measured. The field lines appeared to concentrate around the areas showing the most dramatic color changes, as if magnetic energy was being channeled toward those specific locations. The transformation reached its peak approximately 7 hours after it had begun. At that point, the previously gray surface had become a patchwork of blues, greens, and regions that reflected light, with an almost iridescent quality. The spectral data showed that nearly 20% of the visible surface had undergone chemical modification. The thermal output had increased substantially, with the object radiating more energy than it was receiving from sunlight, a clear violation of passive thermal balance. Particle detectors registered their highest readings during this peak period. The stream of organic molecules escaping from the crater region intensified into what could almost be described as a jet, though it lacked the violent eruption typically associated with cometary outbursts. This was a controlled release, steady and sustained rather than explosive. The chemical composition remained remarkably consistent, maintaining the same ratios of hydroxyl, carbon dioxide, ammonia, and cyanide compounds that characterized the initial observations. Then, as abruptly as the transformation had begun, it stopped. The color changes halted mid-progression. Areas that had been actively shifting from gray to blue-green froze in their current state. The thermal signatures began declining, dropping back toward equilibrium with solar heating. The magnetic field fluctuations that had grown increasingly complex started to simplify, returning toward the baseline pattern observed during the initial approach. Within another hour, the spectral readings were fading. The newly formed chemical compounds showed signs of breaking down or reverting to more stable configurations. The vibrant colors that had spread across the surface dimmed, and the gray tones began to reassert themselves. The particle stream from the polar crater slowed and then ceased entirely. The faint luminescence along the plate boundaries vanished, leaving the surface looking much as it had before the activation, though subtle differences remained for those who knew where to look. The magnetic field completed its regression to the simple pulsing pattern within 3 hours of the peak. All the complexity, the overlapping frequencies and concentrated field lines, disappeared as if they had never existed. Instrument logs showed a clear timeline of escalation followed by rapid decline, like a biological system entering an excited state and then returning to rest. What remained unclear was why the transformation had ended. No external trigger was apparent. The spacecraft hadn't changed its behavior or stopped transmitting signals. Solar conditions remained stable. The object had simply chosen, if that word could even apply, to cease its response and return to dormancy. The 7-hour window of activity had provided an enormous amount of data, but it had also raised far more questions than it answered. 3. iAtlas had demonstrated an ability to respond to examination in ways that seemed purposeful and controlled, activating systems that released the chemical building blocks of life before deliberately shutting down again. Mission Control initially assumed the spacecraft had suffered some kind of technical malfunction. Instruments operating in deep space face constant challenges from radiation, temperature extremes, and the accumulated stress of months or years away from Earth. Calibration drift and sensor failures are routine concerns for any long-duration space mission. But as engineers examined the telemetry in detail, they found no evidence of hardware problems. Every onboard system reported nominal function. Power levels remained stable. The communications array was operating within normal parameters. Yet, despite all systems functioning correctly, the flow of scientific data had simply stopped. The probe continued transmitting basic housekeeping information, the routine status updates that confirmed it was still operational and maintaining its trajectory. But the cameras had gone dark. The spectrometers weren't recording. The magnetometer, which had been tracking the object's magnetic field variations for days, now showed only flat baseline readings. Even the thermal sensors, which should have continued registering the object's infrared signature regardless of any other failures, returned empty datasets. What made the situation particularly unusual was how simultaneous the shutdown had been. One moment, all instruments were collecting data as expected. The next moment, they had all stopped at precisely the same instant. Equipment failures don't typically occur with such coordination. Individual components fail independently based on their specific vulnerabilities and operating conditions. For every sensor and camera to cease functioning at exactly the same time suggested something other than random malfunction. The last coherent readings from the magnetometer showed a small spike, barely above the detection threshold, occurring in the final seconds before all instruments went silent. This spike didn't match any previously observed pattern. It was brief, lasting only a fraction of a second, and it appeared across all three axes of magnetic measurement simultaneously. Then the instruments shut down in sequence, one after another over the span of about 2 seconds, as if each sensor was being individually switched off. Tracking stations on Earth continued attempting to communicate with the spacecraft, sending command sequences that should have triggered responses from backup systems or initiated diagnostic routines. None of these commands produced any effect. The probe remained silent apart from its basic status beacon, which continued broadcasting at regular intervals. That beacon confirmed the spacecraft was still functional, still powered, still maintaining attitude control. It simply wasn't observing anything anymore. Meanwhile, ground-based telescopes continued monitoring 3I Atlas itself. These observations revealed changes that were difficult to interpret without the close-range data the probe had been providing. The light curves that astronomers use to track an object's rotation and brightness showed that the characteristic flickering pattern had disappeared. Previously, the object's brightness had varied as different surface regions rotated in and out of sunlight, creating a predictable rhythm of brightening and dimming. Now the brightness remained constant, as if the object had stopped rotating entirely or its surface had become uniformly reflective. Thermal observations from infrared telescopes showed no more temperature variations across the surface. The pulsing heat signatures that had appeared during the activation phase were gone. No outgassing jets were visible in any wavelength. The object appeared completely inert, indistinguishable from an ordinary chunk of rock and ice drifting through space. All the unusual characteristics that had made it so fascinating had vanished. However, precise astrometric measurements revealed something subtle but significant. When astronomers calculated the object's position based on its known trajectory and compared it to actual observations, they found a discrepancy. 3. Atlas had shifted approximately 100 kilometers off its predicted path. For an object traveling at tremendous velocity through the solar system, this represented a noticeable deviation that couldn't be explained by measurement error or gravitational perturbations from known bodies. Several mechanisms could potentially account for such a trajectory change. Comets routinely alter their paths through outgassing, as jets of vapor act like tiny rocket engines, pushing the nucleus in various directions. But all observations confirmed that 3I Atlas had stopped releasing material before the trajectory shift was detected. Another possibility involved mass ejection, where pieces breaking off from the surface could alter the object's momentum. Yet no debris field was detected in the vicinity, and the object's brightness hadn't changed in a way consistent with losing substantial mass. The most puzzling explanation, and the one that some mission scientists quietly considered, was that the shift had been controlled. If the object possessed some form of internal propulsion, whether through directed gas venting or other mechanisms, it could have adjusted its own trajectory. This speculation remained largely unspoken in official reports because it implied capabilities that no natural object should possess. 2 weeks after the instruments went silent, something unexpected occurred. The mission's communication team received a transmission through an auxiliary antenna system that hadn't been active since shortly after launch. This low-gain antenna was designed as a backup communication channel, typically used only during emergencies or specific operational phases. It had been dormant throughout the encounter with 3I Atlas, making its sudden activation difficult to explain. The signal contained a single compressed data file with no accompanying metadata. There was no timestamp indicating when the file had been created, no system identification header showing which instruments had generated it, and no coordinates linking it to a specific location or orientation. The file simply existed, encoded in a format consistent with the spacecraft's imaging system, but transmitted through a pathway that shouldn't have been active. When engineers decoded the file, they found it contained one image. The photograph showed the upper horizon of 3I Atlas, captured from a low angle that suggested the spacecraft had been in the process of moving away from the object. The lighting was dim, dominated by reflected sunlight rather than direct illumination, casting the surface in shades of gray and deep shadow. But across that shadowed horizon, something was visible that hadn't appeared in any previous image. The surface, which had appeared relatively smooth in earlier photographs, now displayed an intricate pattern of interlocking geometric shapes. The hexagonal plates that had characterized the surface throughout the mission were still present, but they were now outlined by faint luminescence. Light traced along the boundaries between plates, creating a network of glowing lines that spread across the visible hemisphere. The illumination wasn't random scatter or reflection. It formed organized patterns that curved and branched according to some underlying structure. The light concentrated particularly strongly around the polar crater, the location where radar had discovered the massive internal cavity. At the center of that crater, where the cavity presumably connected to the surface, A circular opening glowed with a distinctive cyan color that stood out against the gray and silver tones of the surrounding terrain. Frame-by-frame analysis, comparing this final image with earlier photographs of the same region, showed that the light was pulsing. The intensity varied in regular cycles, brightening and dimming in a rhythm that matched the 9-hour rotation period the object had displayed initially, but compressed into a much faster tempo. The pattern played out over approximately 12 seconds before the image ended. During those 12 seconds, the light expanded outward from the crater, spreading across the visible surface until it bathed the entire area in a uniform field of blue-green illumination. Then the transmission ended. No subsequent images followed. No additional data arrived through any communication channel. The spacecraft vanished from tracking networks entirely, no longer responding to commands or broadcasting its status beacon. Debris tracking systems that monitor space for fragments of defunct satellites and mission hardware never detected any trace of the probe.